Oh my god, Jenny, I had the weirdest dream last night. Like, there are these 3 ghosts.
Who are you?
I'm getting tired. I'm just gonna take a nap.
No sleeping in class.
And that's why children never sleep in class. In today's presentation, we will not be talking about muons.
Right, so today for our presentation, we're going to be talking about force shields.
Adiabatic force field? No, Billy. These types of force fields are used in the military and in future space travel. Now, for our presentation, Colin will be getting in depth in the physics behind the space travel force fields, while Billy and I begin to talk about the actual practicality of wartime space force fields. Adiabatic. Hope you enjoy our presentation. Yeah.
3D. Oh.
Alright, now first we're going to talk about the Raphael trophy systems, which goes on top of tanks and armored vehicles, and it creates kind of a force shield around. I'll just draw a picture and explain it from there. Oh god. Oh. Alright, here we go. Draw a picture here. So you got a tank, rectangle tank here. Here's the tracks that it goes on. And you got the top, the gunner sits. Got the gun coming out. Then the Raphael trophy systems can go on either on the back or on the top. We'll just put it on the top since it's easier to draw. Kind of like a square. Really what it does is when you have incoming missiles that people shoot at you, like RPGs. We got a guy here, John, he shoots it at it. The Raphael trophy system can detect it all the way around the tank, and then it shoots kind of like a shotgun blast at it to explode the missile incoming. So this really helps out when creating tanks because you can make them a lot lighter because they don't have to be so protective of rockets when you have the trophy system sitting on there, because then that'll just destroy everything. And it can turn, it detects everything all the way around it, so you can, even if being shot from the back, you're still covered, so we can save a lot less money on paying for armor on the tanks.
Now, before I begin, I'd like to show you a homemade video of what I will be talking about looks like. Well, now we'll be moving on to less of a radar-based force shield into a more electromagnetical-based force shield. Now, the force shield I'll be talking about is the supercapacitor electromagnetic force field that was created in Britain in 2010. Now, this force shield takes electricity impulses that is sent through a supercapacitor, which then turns into electromagnetic energy, which is allowed to repel bullets. The way this works is that the supercapacitor is folded like a fabric in between the armor and the actual tank. Now, because of this, like the Raphael system, it allows for the tank to be extremely light and extremely mobile. Now, when the electrical current is run through the supercapacitor, it releases a moment of electromagnetic pulse. This electromagnetic pulse, if timed correctly, can slow down or even repel bullets, RPGs, and other projectiles that are shot at the tank. Because of this, the bullets get blunted and start spitting off. Is there a clown behind me? Oh, hi, Mr. Wilson. So, where was I? Ah, yes, the blunted. Now, if this timed correctly, the bullets become blunted and spin off, creating a much slower velocity and so no penetrating damage to the tank. However, unlike the Raphael system, this needs to be timed extremely precise. If not timed precise, it could be too soon or too late, and the bullets will continue on. However, they do have the technology, which is way too complex for us, I'm sorry, kind of is, to determine when this needs to be sent, so it does work. The problem with this is there is a slight recharge time on the supercapacitor. Because of this, there is a moment where if they were to shoot simultaneously, say RPGs, the tank system would be at a loss. However, since they are allowed to charge it rather quickly and with a small amount of energy. So, in a sense, this is the future of electromagnetic force fields within the military. So now I'm moving to Colin, who will be talking to you about plasma shielding in space.
Hey, look, Alec Master Chief. Alright, for my part of the presentation, I'm going to be talking about force shields dealing with space travel, and I don't really have a spaceship looking thing like the Lego tank I used in the supercapacitor part of the video, so I'm going to pull Khan Academy on this one. So here we go. Alright, here we go. Gonna open up some paint. Gonna draw some space and oh, here we go. Gonna draw the Earth with a nice shade of blue. Yeah, no, oh no, okay. Maybe I should speed this up a tad so we can get on with the physics. Maybe some orange. Okay, so we have Andy as our astronaut. Okay, she's not in our class, but anyways. As space travel begins to move out of the Earth's magnetosphere, astronauts are no longer protected from the energetic particles filling the interplanetary medium. I mean, unless you're Master Chief, then you're pretty well protected. He's kind of a boss, seen earlier in the video. But anyways, these energetic particles can reach tens of mega electron volts per nucleon, which presents a pretty bad radiation hazard. Somebody brought this up in class about how the radiation can lead to Alzheimer's, so I mean, it's not that much of a hazard, but I mean, alright. There are two primary sources of the most energetic particles, and those are the galactic cosmic rays, or GCRs, and solar energetic particle events, known as SEPs, and these are caused with solar flares. GCRs are made up of 85% protons, 14% alpha particles, and 1% heavier nuclei. So you might be thinking, well, hey, 1% isn't that bad, but you know, these heavy nucleons can make you forget whether or not you put a cat in a box. The flux or flow of these GCRs is pretty constant in the heliosphere, but there is some modulation during the solar maximum. If you're wondering, the solar maximum is a period during the 11-year solar cycle. It lasts for a few days where the solar activity is greatest, increasing irradiance. Even though this decreases the flux of GCR, there is a sharp increase in SEPs to around 100 mega electron volts. So traveling during this would probably be highly not recommended. Oh my derp. Traveling in this probably isn't recommended, but I mean, go for it if you want. How do we get around becoming potatoes, you might ask? Well, there's two main ways we can go about blocking these particles from getting to our brains. One, we could draw an awesome shield like this, or no, one way is to provide a sufficient enough barrier between you and these particles. This would involve putting 20 grams of lead for every square centimeter of your spaceship, which is pretty impractical for a couple of reasons. One, that's a lot of lead. This would increase the mass of the ship so much that it's not even, just no. Okay, second, the particles are stopped with direct interaction of the lead nuclei. So this could create secondaries that are also radioactive, which would kind of defeat the purpose of trying to shield out the energetic particles. So that idea is kind of out. The second way you could do this is blocking it with a high-powered magnetic field, and this would be pretty awesome because no secondaries are produced, but this would require yet again a large mass and high power requirements, or have a very large field coil, which wouldn't be that great either. Luckily, there's a third way we can block these particles, as far as we know, and it's kind of a variation of the second, but there's been suggestion of deploying a plasma-inflated magnetic bubble or mini magnetosphere. This kind of uses the same idea as the Earth's magnetosphere, but shrinking it down to the size that we can just surround a ship. So there's actually a project taking place testing this at the University of Washington, The scheme's called mini magnetospheric plasma propulsion, or M2P2. This uses the concept that collisionless plasma can contain a magnetic field frozen inside itself, as seen by my awesome picture. As the plasma expands outward to form a bubble, it will generate the currents necessary to carry the B field with it. So basically you could have a bubble shield with a magnetic current around your entire spaceship, which is pretty awesome. The plasma bubble continues to expand until the outer pressure from the solar wind is equal to the net pressure of the inside of the shield. And this expansion would range from about 10 kilometers to about 100 kilometers. This cross-sectional shield would substantially increase the interaction with the charged particles without the need for supermagnets or large current loops, as I mentioned earlier in the video. So it's a pretty good idea. I think scientists should do this. The M2P2 was originally tested through computer simulations. Yes, this is supposed to be a computer. Not as good at drawing as Mr. Olsen and his hammer, but I mean, maybe I'll try that later in the video. I don't know. Anyways, it was tried with computer simulations at first, but then a prototype was developed to be tested in a vacuum. The prototype was a 2-meter system with a cylindrical magnet measuring 10 centimeters in radius and 10 centimeters in height. As you can see in these pictures, this is the testing chamber vacuum that was used for the prototype to sit in and where the tests were done. I'm going to show a video clip of the test in just a moment, but helium plasma was inserted into a 3-centimeter diameter circle at the top of the magnet, and in this video, it shows the expansion of the plasma around the magnet, and magnetic flux was shown to be removed from the inner region of the dipole and transported to the outer regions, making a magnetic bubble shield around the magnet, which suggests that this works, which is pretty boss. Sweet, so we could just continuously have one of these magnetospheres encompassing our ship to keep the radiation out, right? Well, not exactly. As the shielding is protecting the inhabitants from bombarding particles, it's also shifting the trajectory of the ship as well as a result of the solar wind. And to deal with this, instead of running a constant shield, there would be pulses of the shield. This would in turn save energy use of the system by not running it all the time. As you can see in my awesome video of pulsing shields, you would think this would leave gaps in the shielding every time there's a pulse so that radiation can get inside, but that's not what happens. Every time the shield is pulsed, it detaches the magnetosphere from the ship and creates a new one. And as you can see from my picture, the ship is constantly encompassed inside the bubble, so it's always protected from the shielding because the shielding expands forward from the ship, and it's kind of self-explanatory. But anyways, this leads us to the magnets that would be used in the future spaceships, and there would be around 100 of the smaller magnets with around 0.05 Tesla, which is pretty high strength magnets. I can't remember exactly what size magnets we used in class earlier this year, but they're a lot bigger. So anyways, these smaller magnets of high magnetic power would be used so that the equilibrium pressure I mentioned earlier can be retained quickly, and the power consumption would stay relatively low at about 1 kilowatt per unit. So there's my presentation. Hope you guys liked it. Yeah. Stay classy, San Diego. Thanks for watching our video.
Yeah, who knows what looks to the future for force fields. Maybe even one day we'll be seeing Star Trek or Star Wars. What?
Alright.